Okay, welcome back. So in the last video we've seen that irreducible representations are quite important to understand aspects of a physical system. So for this video what we're going to do is we're going to see some techniques to kind of find all the irreducible representations of a finite group. And a central ingredient in this is an orthogonality theorem that I will describe and prove for you, which is actually kind of surprising. A special case of the orthogonality theorem is a property of characters of a group that I'll define, and I'll draw some consequences of this. Good. So here is the orthogonality theorem. So what does it say? So let D and D prime be irreps, irreducible representations, on two different vector spaces, the irreps. Then we have the following formula for the matrix elements of these irreducible representations. So if I take the sum over all elements in the group of the following product, so D, the inverse element of G, and then I look at the matrix element Ij multiplied with another matrix element of D prime, so D prime of G K L. So where here I, J run from 1 up to n, where n is a dimension of V. So suppose that V is really just Cn, and V prime is Cn prime. So K and L run from 1 up to n prime. Then this combination is completely determined. So it's equal to 0 whenever D is not equivalent to D prime, and whenever D and D prime are the same, so not just equivalent but just exactly the same representation. So then here I essentially get a square of a matrix element. Then it is given explicitly, let me check, by G, so the order of the group, divided by the dimension of the representation of D, but only when I look at one particular matrix element, so meaning in this case that J should be identical to K and I identical to L. Okay, so this is the orthogonality theorem, and it's really quite a miraculous statement. So it says that if I take any irreducible representation, so that assigns matrices D of G to each element G of the group, I take any element out of this matrix, so I pick just one position in the matrix, and I essentially compute the inner product of this matrix element with the matrix element of an arbitrary different representation D prime, again an arbitrary element within that matrix, then it's going to be orthogonal to that. Maybe I should make this a bit more precise, so let's draw some consequences of this theorem before we prove it. So here's a consequence. And to make the best use of this consequence, it is actually natural to look at all possible complex functions from the group to the complex plane. So let's write, or let's look at this set of functions g to c. So this is a linear vector space. Why is that? Well, I can just write this, if I just choose an ordering of all the elements for the group as a vector, I can simply write this as a vector where each of the entries in the vector are just the values associated to the group elements. So up to fg sub index the order of the group. So this is just saying that this is like c to the power the order of the group. So this is a linear vector space, and that's a bit superfluous, which also naturally has an inner product with inner product. If I have two such functions, what I just do is I sum over all the elements in the group, take the complex conjugate of the evaluation of f at that element times the evaluation, okay, maybe g was not the best letter to use here, let's take h evaluated at that element. So really you should think of this as a Hilbert space. It's a linear space together with an inner product, a complex inner product like this. Okay, and now what I want to do is I want to say something about all possible irreducible representations of a finite group G. So to be sure, in this whole video, G is going to be a finite group. Otherwise, it does not necessarily make sense to sum here of the elements of the group. So this is going to be important. So suppose I can really list all irreducible representations, so all inequivalent reducible representations. So suppose d1 up to dk are all inequivalent irreps of G. Then naturally, out of these irreducible representations, I can build some functions that live in this vector space. So then I can build some functions fij a from sorry, not from C, from the group elements to C are defined by, well, just taking the matrix element, so evaluated at the group element G is just taking the eighth irreducible representation of this element G and then the ijth element in this matrix. Okay. So what does it satisfy? So it satisfies, let's see in terms of the inner product. So if I take f I j a f k l b, okay, and I want to make something more specific here, so I say all inequivalent irreducible representations, let me also require that they are unitary. And I'm allowed to do so because we saw that any representation of G, any of a finite group, is actually equivalent to a unitary representation. So I can always find a complete list of irreducible representations that at the same time are also unitary. So then, if I write down what this inner product of these two explicit functions are, so it's a sum over g, and then so the d a g I j complex conjugate d b g k l. But I know that this is a unitary matrix, so this is the same as taking the transpose. So this is the same as the taking the transpose and the inverse. So DAG inverse JI right, so the taking a j-ith element of the inverse of this matrix. But since this is a representation, the inverse matrix DAG, that's exactly the representation of the inverse element at ji. So we see that this sum here is exactly the one that we had in the orthogonality theorem, where now d prime is d of b and d is d of a. So we can immediately evaluate what this inner product is. It is 0 if a not equal to b, and if a is equal to b, then it's given by this formula. So it's given by g over dimension of the eighth irreducible representation. Right, and then delta jk delta I. Okay, but here, see, the two indices are actually swapped, so this is not delta of jk. It's the delta of I and k, delta I, k, delta j, l, if a equals b. Okay, so just to summarize, this is g over na, delta a b, delta I, k, delta j, l. So these particular functions that I build out of all these irreducible representations, they are all orthogonal to each other. So Fija for a running from 1 to k, if I have k irreducible representations, and I and j running up from 1 to the dimension of this representation a, are all orthogonal. Right, so I've got a whole lot of vectors in this vector space of dimension, the order of the group, that are all orthogonal to each other. So that means that there cannot actually be that many irreducible representations of this group. In fact, okay, we've written down many vectors that are all orthogonal to each other, so there have to be fewer of those vectors than the dimension of the group. So we deduce directly from this that, okay, how many are there here? So I have a sum of a is 1 to k for each irreducible representation, and then I have na squared of such vectors, na squared. And these all have to fit into this order of g dimensional vector space. So we immediately get this inequality. The order of the group. Okay? So in the exercises, you will show that we actually remarkably have the equality here. So the order of G is really the sum over the squares of the dimensions of the irreducible representations. So whereas before, I mean, we did not even have a clue whether there was just a finite number or perhaps even infinite number of irreducible representations. Now we actually get a very strict criterion for the dimensions of possible irreducible representations. Okay, so, last week we looked at the group of order 3. Well, there's only one way to write 3 as a sum of square numbers, right? That's 1 plus 1 plus 1. So this formula immediately tells you that there are exactly 3 irreducible representations of this group, and they're all one-dimensional. And actually we saw them. We had the trivial representation. We had this representation with the complex numbers, so the third roots of unity. And then we had a complex conjugate of this. So these are exactly all 3 representations of this group. In the exercises you'll encounter one example of a group where from this formula you can determine representations that are not necessarily all one-dimensional. Okay, so this is really a very nice formula, and it's a direct consequence of the orthogonality theorem. So let me proceed and prove this theorem. And I should say that the proof of this theorem is not exam material. So feel free here to skip a bit of the video until I finish the proof. But maybe you think this is interesting, and then stay tuned for now. Okay, so let's prove this. Okay, and the first thing I want to do is an intermediate result. So here's a claim. That's quite useful. And it's kind of characteristic for many proofs that occur for groups, actually. And it has to do with averaging things over a group. So here is the particular averaging that I'm going to use. So if X is an arbitrary linear map, so if you like, it's a n by n prime matrix, complex matrix, then there is a natural way in which I can average this linear map or this matrix over the group as follows. So I get a linear mapping A now, or again an n by n prime matrix, that I get by summing over all elements of the group of X here, but where I transform by this these irreducible representations on both sides. So before I act with X, I'm going to transform in the V vector space. So I'm going to take D of G. That gives me a vector in V. I apply X, I get a vector in V prime, and then I can transform it with D prime. Now this is not exactly what I want to do. I want to transform it with the inverse of this group element. So this feels a bit like a conjugation, multiplying from one side with G and the other side with G inverse. So I claim that this new linear mapping, so this is again a linear mapping from V to V prime, or a n by n prime matrix, it intertwines D and D prime. Okay, so let's quickly see why this is the case, and it's a matter of just checking here the property. So indeed, let's see, so we have to check that composing on one side with D is the same as composing on the other side with D prime. Right, so I take let's see, DH or D prime H A, and I want to show in the end that this is equal to A D of H, right? If that is true for every element H in the group, then A indeed intertwines D and D prime. Okay, let's just insert the expression here, so I get a sum over the group elements G. Then I have my D prime H, D prime G inverse X, D of G. But because this is a representation, this is the same as the D prime of H, G inverse. But this is I can also write it as the D prime of, let's see, the inverse of G H inverse, right? If I take the inverse and I interchange the order and take the inverse of both elements, it gives me an H G inverse. Okay. And I want to do something to make this look like, again, a D prime of G inverse, so it's nearly that. The only thing I have to do is to change variables here from GH inverse to some new element G prime. So I'm going to write G of prime is GH inverse. So here I was summing over G, but we know, because this group has an inverse, that multiplying all elements of the group by this fixed element H inverse again gives us all elements of the group. Right, so this is the same as summing over G prime in the group, where now I have D prime of G prime inverse. I get an X, and then I have D of G here, and G was G prime times H. I get G prime H. And well, essentially we're done now, because this expands to D of G prime times D of H, but that is exactly the expression I had up there. Well, after I relabel G prime to be G again. Okay, so I have, for any such linear mapping, I get an intertwiner. And whenever I have an intertwiner for two irreducible representations, I have Schur's lemma. So the two parts of Schur's lemma combined, they tell us that if D and D prime were not equivalent to each other, then this linear mapping has to vanish. And if D is really identical to D prime, then A had to be a linear multiple of the identity matrix. So the identity matrix of the dimension of D, so n. And here actually it's useful to actually determine what is lambda. And And a natural way to determine this is just take the trace on both sides. Right? The trace on the right hand side is just n times lambda. And here I get the trace of A. So I get that lambda is 1 over n trace of A. Okay, so let's just compute this. So this is 1 over n, sum over the group elements, and then the trace of this part. But remember that d prime of g inverse is really the inverse of d prime of g times x d of g. But this trace, since a trace is cyclic, this is just the trace of x. I can take my d of g, which is from the back to the front without changing the trace, so it will cancel this part, leaving me just with the trace of x. So really this trace here is independent of my group element. So I just get a factor here, which is the number of elements of the group. So I get the order of the group divided by the dimension of the representation times the trace of this matrix X that I had chosen. Okay, so far so good. This is a nice result on arbitrary linear mappings X. But how is this useful in proving the orthogonality theorem? Well, for that we're going to choose a very particular convenient form of this linear mapping X. Okay, so this was an intermezzo. So choose conveniently X to be the following mapping. So X is going to be this matrix with just a single non-zero entry. So everything is going to be equal to 0 except somewhere here where I put a 1. And let me say explicitly that this is at the entry k, j. So in kind of more, say it's a quantum mechanical notation, you would typically write this as a ket followed by a bra in this form. So I take the inner product with the basis state labeled by k, and then I take that inner product and I multiply that with the basis state j. Okay, but this is just a particular matrix with all zeros but 1, where I take j and k for j and k fixed. Okay, and in particular j has to run from 1 to n, and k has to run between 1 and n prime. Does that make sense? No, it should be the other way around. Like this. Because whenever I give it a vector living in V, it has to be able to take the inner product with k. So k should really run from 1 to n, being the dimension of V. Okay, so let's just determine what the consequence of Schur's lemma is when applied to this matrix X. In particular, what is the matrix element of this averaged version of X? So then A evaluated at matrix element I, L. So this is, if you like, sum over the group elements. I want to take the matrix elements, so that's like sandwiching it between a bra and a cat at I and L. And then here in the middle I get a D G prime inverse J. Here I get a K D G. Okay. But these are just the matrix elements. So this is just DG inverse IJ. And this is the DGKL matrix element. Right, so this is exactly what I wrote up here. So this is the sum that we want to evaluate. So this choice of X was pretty clever indeed, now that we see it. And we know explicitly what the answer is going to be, depending on these two cases. So indeed, it's going to be 0 when these two representations are not isomorphic. And if they're identical, it's going to be equal to, so 0 is going to be equal to G over N trace of X. Right, times, let's see. Okay, so there is an identity matrix here. So I'm taking the IL component of the identity matrix. So there is a delta IL for that, because those are the matrix entries of this identity. So the only thing you still have to do is to evaluate the trace of X. Now, since X only has a single component 1, it's easy to find this trace, so it's only going to be equal to 1 if it's on the diagonal. So when J and K are equal. So this is delta J K. Right, and that was exactly the answer that we wanted to have. So this finishes the proof of the orthogonality theorem. Okay. Let's erase a bit the proof again. So if you skip this part of the video with the proof, then this is the right time to zoom in again. And we'll just continue whether we have not done the proof. So, I mean, in principle, this allows us to determine whether two representations are equivalent or not, just by taking some of its matrix elements and then just checking whether all of them are 0 when you take this inner product or not. But actually, there is something slightly more practical that one can do here. And it takes advantage of the fact that here, with these matrix elements, they are going to change when you're going to do a similarity transform. Because a similarity transform is just a change of basis of your vector space. So certainly the matrix elements are going to change under such a change of basis. So we want to look at something, a property of a representation that does not change under a similarity transform. A natural thing that does not change under a similarity is the trace. So this is what characters are about. Characters. So we finished this part. Now let's look at characters. Okay, so definition. The character which is really a function from G to the complex numbers of a representation D of the group GL phi is given by just taking the trace of the matrix that you've associated to a group element. So chi of D at the group element G is the trace of the matrix assigned to that group element. Okay, so this is pleasant because if D and D prime are equivalent, then their characters are going to be the same. Then chi of D as a function is really the same as chi of D prime. Right? Because if I look at the trace of D of G, it's going to be related by a similarity transform to that of D prime, so I have a S D prime G S inverse. And as we just saw before, this S and S inverse, they cancel each other, so I get the trace of the D prime of G. So that's pleasant. So actually something more precise is true. So here's another theorem, which is really the orthogonality of characters. If D and D prime are irreps of a group G, then the inner product, in the sense as I introduced before, of chi of D prime. So let me write that out again. So it's the sum of the elements of the group, the complex conjugate on this side. So this is a comma, right? Times the character of D prime. Then this is going to be 0 if D and D prime are not equivalent, and it's going to be the order of the group if they are equivalent. So as you can see, this theorem is slightly more powerful than the orthogonality theorem for the matrix elements, because it also says something about when D and D prime are equivalent but not exactly identical. So here I really had to assume that D and D prime are identical to get this result. Here really it says something about arbitrary irreducible representations. Okay, and the proof is very straightforward, starting from the orthogonality theorem. So first of all, we may assume that D and D prime are unitary, because we know that they will be equivalent to unitary representations, and really the characters that I'm comparing, they do not depend on what particular representation I choose, as long as it's equivalent. So we may assume D and D prime are unitary, and we may also assume that that they are actually identical if they are equivalent. So suppose that they are equivalent, then I know that their characters will be identical, so I may as well just start with two identical representations. So then this particular inner product is given explicitly. Let's just work it out. So it's given by taking the trace of these matrices. So I have to sum over the indices of the first one and over the second one of this matrix II and D prime G J J. Okay. And then we notice that what we've written here, because we've assumed it to be unitary, is the same thing as D of G inverse II. So we're exactly in this setting, except that we're now summing over I and j set equal to each other in K of L. So it's certainly 0 when D is not equal to D prime. And if it is equal, then so I get explicitly G over N. I still have a sum over the group, and a sum over I. Not a sum over the group, sorry. Still have a sum over I and j of delta jk, so that is ij, and delta il, so the first and last index, is also ij, delta ij. Right, but this is this just sums up to n, right? Because I and j, they run up from 1 to n. So it cancels the factor in the denominator, which is exactly what they had there. So this is when they are equivalent. Okay. So this is quite nice. So if you find any irreducible representation and you want to know whether it's different or equivalent to a representation that you found before, the only thing that you have to do is to determine the character. So you take the trace of all the matrices that you've determined, then you take the inner product of this set of numbers, so there are order of G numbers there, and you just see whether it's orthogonal to the ones that you found before or not. If it's not, then you've really found a new irreducible representation. So there are a couple of consequences here that I'm going to write down before finishing. So consequences. Here we go. So we know that for an arbitrary representation D, we can decompose it into irreducible representations. So we have that D is equivalent to, well, a number of copies of one of the irreducible representations, then a number of copies of another one, and perhaps there are like k different irreducible representations appearing in the decomposition. So this is like the decomposition that we did explicitly in the last video for the quantum mechanical application. So we know that this is always the case, where D1, 2 up to k are irreducible representations. And given this, we can easily compute what the character of D is going to be. So then the character of D evaluated at G, so that's a trace of D of G, which we know is going to be the same as the trace of the transformed representation, so this one, because they're equivalent. But whenever I have a block diagonal form and I want to compute the trace, well, it's just taking the sum of the traces of the blocks. So this is really the sum over A equals 1 to k, and then each block occurs, so let's say it occurs m sub A times, so I get ma times trace of dA of G. So this is really the sum over A, ma times the character of this representation. So whenever I have a decomposition, my character as a function, it is really just a linear combination of the characters of its components, where the linear prefactors are simply the number of times that this irreducible representation occurs within the decomposition. And since all these characters are orthogonal, or if I even divide this inner product by the order of the group, they're going to be orthonormal, I can easily extract what these numbers are. So a consequence is that m of A is up to this normalization by 1 over the order of the group, given by the inner product, if you like, of so chi dA with chi of D. Right, so as soon as you've classified all irreducible representations of a group, and somebody hands you a new representation of which you don't even know whether it's irreducible or not, you just have to compute its character, take the inner product with the characters that you already had, and it will tell you immediately how often this character or this representation is inside of your new representation. And just a final remark, in the exercises, you will show that this very particular representation that we introduced last week, which is the regular representation, the regular rep D equal to D regular, contains each irrep D of A exactly ma times. So we're ma, but that is by definition exactly ma equals ma times, where ma is a dimension of this irreducible representation. So in particular, this regular representation that you can always write down for a finite group, it contains all irreducible representations, and most of them more than once, namely a number of times equal to its dimension. So this is one way, if you're just given an abstract group, in which you could actually determine all irreducible representations. Although for a large group, the regular representation is really a huge object. So actually there are mathematically more convenient ways to determine all irreducible representations. But for now I think this is sufficient, and in principle will allow you to do whatever you would need to do in order to determine them. Okay, so that's all for this week. See you next week.